Well, you may be noticing that a lot of the axioms you seem to get for free, right? I mean, there's this thing that happens with subspaces, and we said, hey, you know, in the last video, 1 and 2 and 5 and 6 and 7 and 8 happen for free. Is there a shorter way to test whether something's a subspace? Because we do it a lot, and absolutely there is. There's the subspace test. So let V be a vector space and W a subset of that vector space. Then W is a subspace if and only if, in other words, if you're a subspace, you get these three things. If you get these three things, you get a subspace. If the 0 is in W, if x plus y is in W for any x and y in W, and if Cx is in W for any C in the field and x in W. We have to prove this two directions. Okay, so first, let's assume W is a subset of V. Sorry, is a subspace. So W is a subspace. So we're assuming that this set is a subspace, and we have to prove all three of these. Now, think about it. If W is a subspace, 2 and 3 are a consequence of the operations in vector space W. Those operations are closed, right? So yes, for any vector space, if you choose two elements in it, their sum is in it. If you choose something in the field and something here, it's the scalar is still in it. What about 3? Well, you know W is a vector space, so you know it has a 0, but does it have the same 0 as V? Since W is a vector space, by axiom 3, VS3, there exists some 0. I don't want to assume it's the same one. There exists 0 prime in W such that x plus 0 prime equals x for any x in W. But we also know, purely in V, that x plus 0, x, it's an element of W, so it must be an element of V, x plus 0 equals x. So remember, if you have two things that act like the identity in the last section, theorem 1.1, 0 equals 0 prime, and it in fact is in W. Therefore, 1 holds, 2 holds, and 3 holds. Okay, let's go back real quick. Now, let's assume we have a subset of a vector space, okay? Assume W is a subset of a vector space, and 1, 2, and 3 hold. As we mentioned before, we have to see, is it now a subspace? In other words, going back to the definition, does VS1 through VS8 hold? VS1, 2, and 5 through 8 hold for all elements in V. So certainly those in W. we really have to worry about two elements in particular. Sorry, two vector space axioms in particular. Notice one, assumption 1 implies VS3. VS3 was the one about having an identity, and we just said, hey, the identity in V is in W, so we get that one for free. Okay, so we're down to 4. That's the inverses. Remember, and maybe I'll put it here just for a recollection, we have to pick an element in the place we want to show as a vector space. So we have to pick, let W be an element in W, right? For any element in W, is there an inverse in W? Well, by 3, -1 times W, which, if you remember from section 1.2, is negative W, is an element of W. And VS4 holds. Therefore, W is a vector space.